Hey guys, so I want to discuss another example here for specific heat. So let's go straight to the question. A piston cylinder device initially contains 0.5 meter cubed of nitrogen gas at 400 kPa and 27 degrees. An electric heater within the device is turned on and is allowed to pass a current of, this is the current in ampere, the time from this is the voltage. Okay, electrical work, remember. The nitrogen expands at constant pressure. Check that it's a piston, so okay, makes sense. There's a heat loss of 2800 joules occurring during the process. Determine final temperature. Okay, so let's first sketch the diagram so that we know what's happening. Okay, so we have a piston. I have the diagram already drawn actually, but I want you to get used to the process. If you don't do this, you might miss out some important information. So what's inside is N2. Okay, so not air, not water, not refrigerant. Initial volume, V1 is 0.5 meter cube. We have P1 equals to 400 kPa. It's constant pressure, so it's equals to P2 as well. T1 is 27 degrees Celsius. Okay, or you can convert this to Kelvin. 27 plus 273. Okay, that's the conversion. So that's a nice 300K. And then an electric heater within the device. So that's just a work E in. Okay, so that's VIT. The V is 120, I is 2 ampere, time is 5 minutes, so times 60, you get 300 seconds. Remember, this will give you the answer in joules. It expands at constant pressure. There's a heat loss happening. So heat loss is simply Q out. Alright? So you have to determine the final temperature of nitrogen. So you want to find T2 with all this given information. So of course we use the energy balance equation. So you start with, actually you can start with the very first equation, this. Okay, and then you expand it to the work Q, work Q, etc. If you are very familiar, then you can start with this. So we have electrical work coming in, this, okay, check. And then we have Q out, okay, minus because it's Q out. And then we have boundary work. Why it's boundary work out? Because that's what we do. You must have it at, you must put it at this direction. It has to be boundary work out. Okay, equals to delta U. Of course, there's no KE and PE. Okay, what happens next is boundary work goes to the other side. Okay, so you won't have this any longer, but you have delta U plus WB. Delta U plus WB will be equal to delta H, right? So this is what we take here. So we have work in minus Q out equals to, straight away, take delta H. And delta H is mass H2 minus H1. Remember, capital letter has multiplied with mass. So this is how you put it, and H2 minus H1 is Cp delta T. H goes with Cp. Okay, why we need to multiply with mass? Because here we need to multiply with mass. Because the equation is solving for this capital H, which means it's enthalpy, total enthalpy, not enthalpy per kg. Okay, Now T2 is nicely in this equation. So you can actually just solve this equation and then find T2. No need to refer back to the property table. Okay, so let's check for the information. WE can be found this way. VIT, we have it here. So VIT is in seconds. Remember, this is in joules. So if you want it in kilojoules, you need to divide by 1000. So we get this. Okay, and okay, before that, then we have this. Q out, we have readily available 2.8 kilojoules. It's Q out. And then what else? We have T1. T1 is 27 degrees here, 300K. CP, of course, from table A to A or A to B. Let's put a pin in that. Okay, we'll come back to that. So it's mass that you are missing. Okay, mass is missing. And because this is ideal gas, how to find mass? It's from ideal gas equation. Please don't use what is that equation? Mass equals to V over specific V. This is not wrong. You can use this, but you will not find the specific volume of nitrogen. Okay, this equation can be used, but if you use this, then based on my experience, students will just take the specific volume of air or water even, okay, which will be completely wrong. So remember, ideal gas, you have to use the ideal gas equation. Okay, of course, it's PV equals MRT. You can find M easily. The P, all these properties will be happening at a certain state. So if you choose state 1, then you can find P1 is 400, is given in the question. There. V1 is given also here, 0.5. P1, V1. R is gas constant. So you can go to table A1, ideal gas properties. Okay, you can even Google this. T is of course the temperature at 0.1. So we have all of this. You can find the mass. Okay, once you have the mass, put everything in this equation. Okay, we will have already, of course we have these two. Mass we have. So what is the specific heat at constant pressure? One more thing that we have. Okay, so the specific heat, here I've written it down straight away. This is the specific heat. So you can of course go to A to A or A to B. So if you're wondering what temperature do you use, let's say you're going to A to B, I will tell you that because you don't know the other temperature, right? So you can't exactly take the average. You only know T1, you don't know T2, so you can't calculate T average. Therefore, you can just use T at 300K, which means you can use A to A. That's fine. Okay, so go to A to A, go to nitrogen gas, you will find that this is the CP. Okay, so put all the values in. As I said, because it's delta T, no need to convert from degree C to Kelvin, but it's a good practice to convert. Okay, so here you can write 300 Kelvin. If you do that, then your final answer will be in plus 273 Kelvin. Your final answer will be 56.7 plus 273 Kelvin. If you didn't change this, then your answer will be in degrees Celsius. Okay, so that's how you use the specific heat. The top part actually is exactly the same as the previous topic, except now we are just replacing delta H or delta U with the specific heat. Okay, and the advantage here is you can, number one, solve for ideal gases. Okay, because the properties are limited in the property table. We don't have a lot of properties for ideal gases. So we use the specific heat. And another advantage is when you want to solve for temperature. As you can see, in this equation, straight away, it will give you the temperature. Okay, so that's another problem solved. Maybe I'll create another one. Another video for you to use as a reference.